Hello, my name's Craig and this is my wing and airfoil design presentation. In this project I needed to design a wing and an airfoil that would suit the requirements set for me. I needed to do research and analysis to justify my decisions and prove them. I needed to produce a scale prototype and I needed to suggest future improvements as revisions. By observing the aircraft data table, you can see what is required for my high altitude, long endurance UAV. Researching how UAVs with similar parameters to mine, they are lightweight, low speed aircraft that fly at incredibly high altitudes. They require high lift airfoils, utilising high aspect ratios and low wing loadings. An example is the NASA Armstrong Helios. It has an extraordinary wingspan of 80 metres and a wing loading of less than 3 kilograms per metre squared. These extreme design features meant that the Helios had to be made from lightweight composite materials such as carbon fibre. It has no taper or sweep, but has a 10-degree dihedral to provide lateral stability. The Helios fulfills requirements similar to mine, so I'll use the research to help enforce design decisions. The first key design feature to establish was wing loading. By benchmarking, or comparing previous designs to current requirements, it appeared that example A and E in the table here are unsuitable for the design. They are likely either low altitude aircraft or high velocity aircraft. Air density is higher at low altitudes, which would increase lift, and high speed aircraft have more effective lift if you consider the lift equation, and less concern for stall velocity. An example of an aircraft like this can be seen in the picture here with a 45 kg mass wing loading and a cruise speed of 38 meters per second. Example B and C use 3.16 kilograms per meter squared, exceeding lift requirements with their higher weight and their lower velocity than our aircraft. But comparing this wing loading with our target max lift coefficient of 1.4, we would have a stall speed of 13.9 meters per second, which is far too close to our cruise speed. Rearranging the stall formula finds that with a CL of 1.4 and a stall speed of 10 meters per second, a wing loading of 1.5 kilograms per meter squared would suffice, similar to example D. A higher aspect ratio is preferred on our UAVs because it will improve the lift to drag ratio. Lift performance is vital in high altitude, low density environments. Benchmarking a range of aircraft provided potential ARs from 22 to 38. For perspective, the NASA Helios had an AR of 31. Considering our wing loading and a weight of 535 kilograms, the wing area will be extremely large at 356 meters squared. An aspect ratio of 38 would create a 117 meter wingspan. By comparison, consider the structural reinforcement required on the Stratolauncher in this picture with its 117 meter wingspan. So this AR would be unfeasible in a lightweight design, so the span needs to be minimised to reduce bending moments. An aspect ratio of 22, however, would produce a large chord length of 4 meters. This would create excessive friction drag and reduce stability. In mediation of these, an aspect ratio of 28 would span 99 meters and minimise chord length to 3.5 meters, balancing structural feasibility and flight performance within the design requirements. I then chose a base airfoil for development. I benchmarked existing aircraft and conducted analysis to find a base NACA 4-digit. Camber and thickness were chosen with the aim of achieving a CL of 0.65 and a CL max of 1.46. A range of NACAs was simulated to ensure the NACA chosen was closest to optimum. 7% max camber was excessive in terms of CL at 0 degree alpha and would abruptly stall at 10 degrees, whereas 6% produced optimal CL for steady cruise. Increasing camber can have a direct effect on CL due to increasing pressure coefficients on the airfoil. 9% thickness showed lower lift-to-drag ratios due to the higher profile drag. 8% thickness was optimal because 7% thickness had larger boundary layer separation when comparing to 8%, causing lower CL max. Different environmental conditions were tested on the NACA 6308 by using the correlating Mach and Reynolds numbers associated with each condition. At higher velocities and lower altitudes there were clear improvements, with 12 to 15% better lift-to-drag ratio, 7 to 15% higher CL max, and 1.5 to 3.5% improvements in pitching moments. But at 30 km altitude, the aerofoil produced only 1.14 CL max, stalling at 6 degrees. And at 10 meters per second, the max CL was even lower at 0.094, stalling at 4 degrees. But this may actually mean the aerofoil has a lower stall speed than required or predicted, but more analysis and real experimentation would be required to confirm this. Adaptations to further the aerofoil's performance. Increasing max camber to 6.5% chord length provided ideal CL at 0 alpha, but max CL is now 1.35 with an early stall behaviour. Observing on-point view in direct design, boundary layer separation was taking place towards the leading edge of the chord, causing an early stall condition. Moving max camber position to 35% chord reduced early layer separation and improved stall behaviour. Max lift coefficient was now 1.56 and stall was predictable. NACA 6308 with 6.5% max camber and 35% chord would be used for the finite design. So upon recording my SLIG format coordinates and converting them into Excel, I then used macros to make a CATIA file. This was then extruded into a 3D object, and a rib was made for structural integrity with some lightning holes and some legs. I then sliced it at a low resolution to provide printing time of 45 minutes, and I printed it, and this is it here. As you see, wing tapering moves the centre of pressure inboards and lowers bending moments, but it also reduces lift and increases the risk of tip stall. How UAVs achieve lift at lower velocities and stability is vital, so a taper of 0.9 will be used. Wing sweep would cost lift efficiency from reduced aspect ratio and once again increase the risk of tip stalling. It's unnecessary for a HAL UAV. So the quarter chord line will remain at 0 degree sweep angle across the span. Wing dihedral will be 3 degrees due to benchmarking. Rapid manoeuvrability is not a priority here. The wings will be high mounted because high aspect ratio ailerons provide high roll force. Stability is preferred priority. The aerodynamic centre and the mean aerodynamic chord were mathematically calculated and later confirmed for accuracy using projected methods as shown in the lower CATIA sketch here. The finite design was reproduced in XFLR5 to be analysed with its variety of flow solvers in order to paint a better picture. For example, lifting line theory neglects dihedral in its equations, whereas vortex lattice method considers it, but neglects viscous effects, and therefore does not show any stall behaviour. 3D panel method is also suitable for testing my aerofoil, but it will neglect viscous effects too. The aerodynamic centre was used as the moment reference point and analysis was made. You can see that the max lift coefficient is still above requirements, and by viewing bending moments you can also see a high structural requirement. Lift degrades sharply after approximately 90% outboard of the wingspan. Inspecting side slip response and rolling moment showed the wing was highly unstable. Increasing dihedral to 10 degrees solved this, but may need reducing once the higher wing is mounted to the fuselage, so further testing would be required here. So the aerofoil successfully achieved a lift at 15 meters per second and would successfully carry a 500 kilogram mass at 28 kilometer altitude. The drag coefficient is 0.002 away from being the lowest achievable, while flying at 0.65 lift coefficient. To improve further, firstly, a wing incidence of negative 0.15 degrees is needed for ideal lift coefficient to be at level flights. Bending moments need to be reduced with tapering. The lost lift could be negated with the winglets to compact vortices. The instability issue was resolved at 10 degree dihedral, although this requires further testing once the wing is mounted high on a fuselage. Thank you for watching.